Hey guys, so I had a question on two of the problems from the fluid sections, problem 6 and 7. So in this video, we're just going to go over those. So looking at problem 6, we have three fluids that do not mix are poured into a cylindrical container with a diameter of 10 centimeters. The density and volumes of the liquids are given. And so like the last one I did, I don't think my values that I used are the same each time. For some reason I look at this, it changes. I guess that's how it's designed. Um, but we'll get the uh, general idea how to solve this. So if we start by thinking about what we're looking at is we have some container and we have a diameter. We're told it's 10 centimeters, and then we have three layers of fluids. So it's kind of just three different fluids. We don't really care what they are because we're told the density and the volume, so that's enough information. So what we saw before previously is the pressure at the bottom of a container with static fluid in it is equal to rho gh, the density of a fluid, times gravity times its height. And that's why I have height 1, 2, and 3 written here because we're going to need to use those. And then we have to add our atmospheric pressure, P naught, to it. So to do this, since we have three fluids, all we need to do is just consider each one of those. We could pull G out in front, and then we're just left with rho 1, H1, rho 2, H2, rho 3, H3, plus our atmospheric pressure. We don't know what H is, so we're going to need to make a substitution for that, but we're given the volume. And the volume of some object divided by its area will give us height, right? Because of three dimensions, we're taking the two that don't matter in this case. All we worry about is the height when solving for pressure from fluids in a container. And so we could substitute that in for our height. We're just putting our V1 over A1. And of course, A is the same. The area is the same for all of these, right? Because it's the shape of the container is uniform as it increases in height. So we pull that A out in front, and we're just left with rho 1 V1 plus rho 2 V2, rho 3 V3, and then plus our atmospheric pressure. So we're not given the area, but we are given the diameter, and we know that area equals pi r squared, or substituting instead of our radius, we could just say d over 2 squared. So we'll substitute that in for our area, and we're left with gravity divided by our pi d over 2 squared and multiplied by each density and volume plus our atmospheric pressure. So these are the values I got, and you'll notice that we just have 9.81 for gravity. In my example, I had a 10 centimeter diameter, so I just moved the decimal over to get it in terms of meters, divided by 2. And then you'll see here that actually, if we look back at our problem, all of our densities are in terms of 10 to the third power, and all of our volumes are in terms of 10 to the negative third. So when we solve that, we don't even need to put those values because they're going to cancel each other out. 10 to the 3 multiplied by 10 to the negative 3 will just give us 1. So I left all of that out because conveniently they made it the same for all of these, and I just multiplied by the coefficients of density 1, volume 1, density 2, volume 2, density 3, volume 3, and then plus atmospheric pressure, which in this case is going to be this. I used 1.01 times 10 to the 5 pascals because of our sig figs. We didn't really need to go any more depth than that, and I just looked that up. It's also on our formula sheet. And so if we plug all that in, we end up with a pressure of 1.12 times 10 to the 5 pascals. So it's not that much greater than atmospheric pressure, but we could see a difference in the two, that it's increased because our fluids, if they're going to be staying in the container, have to be less dense than air, so they're going to increase the pressure, which isn't going to be the same in our next problem. So the other problem I was asked about is number 7 in the fluid section. So we can see here that we're starting with a tube on the left in the diagram. We have both ends of it open to atmosphere, and what happens is that we have that fluid at the same height on this ruler. And then we're going to attach the next figure, we're attaching a balloon to that tube, and the balloon has some sort of pressure greater than atmospheric pressure, we know, because it's actually pushing the fluid up, trying to push it up out of that open end of the tube. And then on the third one, it's the opposite, where we have a vacuum pulling on one side of the tube, and it's actually sucking. In the third case, it's mercury, is pulling that mercury up into the tube. So our goal is to find our gauge pressure and our absolute pressure of both of those. And gauge pressure is just the pressure you would see on a gauge. Generally, you don't, when, let's say you have an oxygen tank, when it reads 0, the pressure is not actually 0 in that tank, it's atmospheric pressure. So that's the difference. And then absolute pressure would be the, so if, let's say that same oxygen tank's empty, the gauge pressure is going to read 0, but our absolute pressure would be atmospheric pressure. So we're trying to find both of those. And so what we could do, we're told that the height difference for both of them is 0.089 meters. So what we could do is, since our answers are in terms of centimeters of H2O and millimeters of mercury, all we really need to do is convert our height measurement into the appropriate, for the problem, the appropriate units. So we would want to convert for the first one into centimeters and millimeters for the other. And then after that, all we'll need to do to get the absolute pressure is add in the atmospheric pressure to the problem. So that's not the right page. Okay, so we start with a height of 0.0898 meters. So in our first problem, let's see if I can get it to pull up. In our first problem, we just need to do some dimensional analysis here. So we're just multiplying our meters of water. This is our change in height of meters of water. And we're saying that there's 100 centimeters in one meter. There should be a 1 here. In 1 meter, and of course that just comes out to be 8.98 centimeters of H2O. And in the second part, part B, they're asking for the absolute. So this A would have been our gauge pressure. So part B is asking for our absolute pressure. And all we have to do is add our gauge pressure to our atmospheric pressure. If you look up the atmospheric pressure in centimeters of water, it's 1,033 centimeters of H2O. And then we're just adding our gauge pressure to that, which comes out to be 1,040 centimeters of H2O. And so on the next one, letter C, we have a negative pressure. Our change in height is the opposite, going the opposite direction because it's a vacuum pulling. So we're going to have a negative for our height. This time it's asking for millimeters mercury instead of centimeters of water. So we just do the same thing, only we're considering mercury in millimeters this time. So we multiply by 1,000 because there's 1,000 millimeters in 1 meter. We're getting the right units then, and that just turns out to be negative 89.8 millimeters of mercury. And so the last one, once again, all we're doing is adding the two pressures together. If you look up the pressure for millimeters of mercury for atmospheric pressure, it's 760 millimeters of mercury. And then, of course, we're going to add our gauge pressure, which in this case is a negative 89.8 millimeters of mercury. And which turns out to be 670 millimeters of mercury. If you guys have any other questions or this wasn't clear, let me know and I'll go into more depth. I guess that's it for today. So take care. I'll be posting another video soon, tomorrow morning. And once again, just let me know if you guys need anything.